in the last clip, we established the idea that there's a ratio or relationship between length scale factors, area scale factors, and volume scale factors. So if we know, for example, that the length scale factor of an enlargement is 4, then we can say that the area scale factor of the enlargement is 4 squared, or 16, and the volume scale factor of the enlargement, you're not going to get there from the 16, you're going to get there from the length scale factor. It's the length scale factor cubed, so that's going to be 64, or 4 cubed. So if I am given, so different enlargement, if I am given that the scale factor enlargement on the area is 25, then to arrive at the length scale factor, I'm going to square root to give me the missing value of 5. And from the length scale factor, I'm going to cube up to get the volume scale factor of 125. Yes, you could raise the area scale factor to the power of 3/2, but my guess is you're going to be happier doing the square rooting and then the cubing. If we are given the volume scale factor, then the easiest way to get back to the area scale factor is actually to go all the way back to length first. So I'm going to find the cube root of 1000, which is 10, and then I'm going to square that to give me an area scale factor of 100. Okay, now what that scale factor means is that you've effectively got a ratio of old shape to new shape. Okay, so you have old shape 1, new shape, scale factor. But you can scale that up. Okay, so it's really a ratio of the measurements between the old shape and the new shape. So we can work with ratios rather than necessarily 1 to a given value of a scale factor. Right, I'm going to draw a little picture here. See if I can illustrate the point. So here's my wiggly shape. Don't know the way it does that. The idea is that we can't work out the areas exactly from the dimensions that I've given. So this is some prism or other, which has an area of 2 square units, a cross-sectional area at the end, and a volume of 20. Over here, I have some other thing which is meant to be similar, and it would have been if I hadn't changed that into an ellipse, where the area cross-section of the end is 18 square, whatever units we're looking for. And we are trying to find the volume of the larger shape. So we are saying, right, we must be given a ratio in one of the dimensions. We might be given a length ratio, we might be given an area ratio, or we might be given a volume ratio. Okay, so we'll be given information to tell us one of that. What we have here is an area ratio. So area is in the ratio 2 to 18. I don't really like the ratio 2 to 18, so I'm going to simplify that ratio. Before I do anything about changing the dimension, anything that's in the form 2 to 18 can be simplified as 1 to 9. These are both area ratios. Now I'm going to change the dimension in which I'm working. I'm trying to get to volume, but it's usually easier to go from area through length. So if the area ratio is 1 to 9, I'm going to square root both of those, square root 1 to get 1. I'm going to square root 9 to get 3. So effectively I have a scale factor of 3 because the other part of the ratio is just 1. So I have a length ratio between the smaller shape and the bigger shape of 1 to 3. It's not the length I'm after, it's the volume. So I want the volume ratio for this shape. I'm going to cube the 1. So I'm cubing the length ratio to get the volume ratio. So my volume ratio is going to be 1 to 27. So the relationships between the volumes are in the ratio 1 to 27. I'm given one of the volumes, so I can now do a proportionality grid. I know that this volume here is 20 in the smaller shape. So I can do an exact proportionality thing up, which will give me a volume for the bigger shape of 540, whatever they are. Well, I'll assume they're centimeters. So centimeters cubed. So I have gone through the different dimensions, looked at the ratio in the first dimension, changed it to the ratio in the correct dimension, and then subbed in the individual value that I was given. Okay, we can sometimes save ourselves a little bit of work here. Let me draw some triangular prisms. Here we go. Okay, so my triangular prism has a length of 2. I will put some centimeters on it this time. And this one, which doesn't look any bigger, but is much bigger because that corresponding measurement is now 5 centimeters. And the volume of the first shape is 100 centimeters cubed. And again, we're trying to find the volume of the second shape. So what I am given is a length ratio. My length ratio is 2 to 5. This does not simplify. Okay, so no simplification of that ratio, but I don't really need to simplify it. I could say the scale factor is 2.5, because I could divide the ratio and end up with this 1 to 2.5. But then when I want to start cubing, that's a bit awkward. 1 to 2.5 is a bit of an awkward thing to cube. So I'm changing my dimension. I'm interested in the volume, so I'm going to go from my length straight to my volume. I should be able to do that. Because you might be looking at this and going, oh, well, I'm going to cube the 1 and the 2.5 over here. It's much easier if you just cube both parts of the ratio that you've got. So my volume ratio is going to be 2 cubed to 5 cubed. So if I simplify that, my ratio in terms of the volumes is 8 to 125. Now I've got the ratio of the volumes and I've got a specific volume measurement. I can stick my volume measurement in for the smaller shape, which was a volume of 100. And when I put that in my grid and find the missing value, I end up with a volume of the larger shape of 1562.5 centimeters cubed. Okay, I've got a couple of exam questions here just to show you how that working is going to look. See if I can find it. Here we go. So the first question says, two similar cones have surface areas in the ratio 25 to 9. So my area ratio is 25 to 9. I'm interested in the ratio of their volumes, but I'm going to go through length. So my length ratio, I'm going to square root my area values. So my length ratio, 5 to 3. Different ratio, but that's right because I'm looking at length, not area. And from my length ratio, I can get to a volume ratio of 125 to 27. I'm told that the volume of the larger cone is 500. So this is the question I'm trying to answer. Once I've got to the dimension I'm interested in, I can use my grid. Now I can see that this is an obvious multiple of 4. So down here, I'm going to have 108 in there, multiplying the 27 by 4. Okay, in the mugs, I have heights of 6 and 9. So I'm given length values or a length ratio of 6 to 9. Don't really like 6 to 9. I'm going to simplify it to 2 to 3. 2 to 3 is easier to work with. I'm then interested in the volume, so I can go straight to the volume from here. So I'm going to go cube the length parts. So my volume ratio, the relationship between the volume in the two different shapes, is going to be in the ratio 8 to 27. So I can put in the volume that I already have. The 324 corresponds to the larger shape, so it goes in that side, and the missing value is 96 centimeters cubed.